The last video was about using vectors to move images. That's not really physics. So this video is going to be about moving things around with vectors.
Ow! I'm studying! I promise!
Acceleration and velocity are very similar things. Velocity, or speed, is a distance traveled in a particular direction over a period of time, where acceleration is some kind of change in that direction or speed over a period of time. We have both of them working as a vector where the unit length is the amount of velocity or acceleration, and you can change that however you like. If you have a direction change, that's also considered acceleration. So a force is equal to mass times acceleration. If you want to make an object move around, that's not already moving, you just apply a force to it, which makes it accelerate in any given direction you have. So a force is just a vector that applies an acceleration to a mass effectively. Mass and weight are not the same thing. Weight is actually a force applied to a mass. It's mass times gravity, which equals force. So mass is the inherent bulk of an object and it keeps it in motion, so on and so forth. That's why a human being in space can be weightless, but they still have kind of inherent mass to them. A force equals mass times acceleration. So what the math works out as is that if you want to have double the force, you can double the mass or double the acceleration. On the other hand, if you want to make an object move more quickly or accelerate more quickly, then you can either half the mass or double the force. Once you get an object moving, then it has something called momentum. So an object in motion wants to stay in motion, this usual physics term. What that means is that if you have a particular velocity of a mass, whether it be 0 or some other large number, it wants to stay in that. The reason why is because the mass is not changing and no other forces are acting on it to change that their velocity. So if you want to have an object change direction, accelerate or decelerate, then you have to apply some kind of force to it. And that's basically what this video is covering. But if we start off with a really simple example, like a ship out in space with no friction, no planets to worry about, no gravity. If you apply a force to this object that's already moving forward, you can make it accelerate or decelerate or turn. So if you do some simple math, we can do whatever you want to it in order to apply forces. Have simple time, which is going to be just 1 second in time, because it simplifies the math for us. We can get rid of those extra acceleration units without having to do any actual math changes. And we can start accelerating it very simple based off of the simple formula in the corner. If we want to move forward and actually apply it to something with a little more meaning, we have a ship that has a particular weight, and we can start accelerating it in order to apply a force. So in this case, we have a force, and it accelerates it from 1 meter a second to 1.5 meters a second. That force is effectively halved because of the mass of the object. One of the temptations is to just divide the overall force by the mass of the object, but you have to be careful with that when you start getting a large number of forces, because now you have to do more division, which is very slow, and then instead of just doing one division at the very end. If you want to make an object turn in this environment, then you can apply a force off to the left or whatever you need. So the obvious one would be having a vector that has the forward momentum, and then you put a 90-degree off to one side with a particular force, and you end up with a slight angle in the flight path. Also notice that the math works out that you actually end up moving forward along that path faster than you were initially. So forces do these things because of the way the vector math works out. So you end up moving faster than you would if you were just moving forward the whole time. So if you ever played an old game, you might have noticed that if you run it at a 45-degree angle, because, well, also you're running faster than you normally would because older games account for that. So that's something to be careful of. You may want to set a maximum length vector so you don't over-accelerate to make the ship fly faster than it's supposed to go. So for accounting for mass, it's really simple just to set everything to 1 and eliminate that particular value from all the functions that you have to code in. It ends up being a lot faster to process. The problem is that if you have different mass objects in your game that are supposed to behave differently in the same environment, now you have to start changing the forces, rebalance everything for every object you have. And that becomes a big mess in the long run. This better solution is just leave the mass in and keep it inside the actual calculations that you work with. If everything is 1, yeah, it's going to be a little slower. But the odds are you're going to have different mass objects anyway. So if you have a small fighter moving around this ship carrier and you have the same forces applied to each one, the little fighters should move around much quicker than the big, large carrier. And you can do that by just changing the mass around. So if you change the example we had before, which was there, and you have a mass of 2 to start with, and you change it over to 10, you can see how the actual calculations with the same force on a new object with a different mass ends up changing its overall characteristics of the game. So dealing with only one force being applied to an object at one time is really pretty limited. It's not very realistic either. So if you have something like a ballistic missile being fired off at an angle, you have to deal with the gravity from the object that's flying over, a planet, for example. So the way you deal with this is this big ugly chart, and you can easily see that there's a mass of an object, it's fired off at a 45-degree angle, and then it has gravity applied to the downward angle. Gravity is calculated by a downward force times the mass of the object. So whatever the object's mass is, you always apply gravity times that particular mass. And then you just apply all those individual forces together, you sum them together, and then apply that to the momentum of the object. In this case, you have 1 second equals a frame, and every frame you see the big burst of force at the very beginning, fired off, and then gravity slowly makes it stop going vertically, and eventually will bring it back down so it starts falling back to the ground. So to keep things looking realistic and slowing down over time, a vacuum in space is not realistic in any way. There's always something acting against an object to make it slow down over time. So we need something called friction to do that. What that is simply a force in the opposite direction of motion that adds to all the other forces along the way. Again, just sum things together. But it actually gets kind of complicated because you don't know necessarily what direction you're traveling before you apply the force. So we can cheat and just apply some small value to the overall end calculation of the momentum at the very end. So like 1 minus 0.2 will end up slowing the object down over time without having to do any real effort whatsoever. Just be careful that when you do this, you count for your frame rate. So if you have 30 frames per second and keep putting on 0.02 as a multiplier, then you switch it to 60 frames per second, it's going to be a vastly different experience for the user. When accounting for time and frame rates is actually pretty simple to calculate. We've been working with 1 second intervals along the way, mostly because it simplifies the math, it's easier to understand, but also because everything is working with the same interval. We can actually just divide by the number of frames per second in order to determine the distance that objects travel in that one frame. Something to account for though is that you want to do it at the end of all the calculations, because if you do it with all the individual forces in the overall process, then you end up doing a lot more math than that is required and the same result most of the time. You start getting into rounding errors and some of these really small forces might actually work out so that they end up not existing at all in calculation. So this kind of remedies a lot of those problems, and it processes faster in the long run. So when working with time, forces, and friction, things get a little unusual. I take the same force and put it all in one big burst and put it in one frame, you end up with something like this little chart off to the side. If I separate that force into 4 frames, then the overall speed at the end is the same, but the distance traveled is vastly different. If I start adding friction to the system, you notice that the actual speed at the end is even different, where the one that's getting 4 smaller bursts of force ended up moving faster than the one that actually got 1 big burst at the beginning. So that's kind of this friction versus distance and time issue. You start looking at this really long list of distances and speeds, you start seeing that over time, the overall path that an object will take simply off of one small change in how a force is applied ends up being vastly different than how it behaves in the game. But the end result is that they actually stop at the same amount of time, and it's going slower and slower, and they stop the same distance away. So it gets a little strange, but depending on what you want in the game, will end up depending on how you want to apply those forces, but it does make a big difference. That's working with basic forces and physics inside the game. Obviously, this is very simple. When you start getting into rotations and combining forces from different sources and having to balance collisions, it becomes more complicated. And I'll be doing additional videos on that later. If it was helpful, please like and subscribe, and make sure to like all the comments you have, questions. Good luck.
Ow! I'm studying! I promise!
Force to it, then you start changing things like a momentum. And I forgot what I'm talking about. The simple little math video.
Bloopers!
Thanks. The last video is about moving.
You're scared of your
No, my brain just shut off.
Breathe.
Yep. Last time we talked about vectors. This video is going to be about using forces. Ow.